This is part 2 of the lectures on relativistic dynamics. Specifically, we now begin to take a look at what is called relativistic mass. Here's how we're going to approach relativistic mass. What I'm going to do is first of all explain to you what it means and what it says. And then I'm not going to do this as a proof per se, but essentially as an application. I'm going to take the statement of relativistic mass and I'm going to apply it to the situation that we looked at earlier in part 1 of this lecture, that is the one-dimensional perfectly inelastic collision. When we take relativistic mass into account, then the postulates of special relativity, all of them hold. Okay, so first of all, what is meant by relativistic mass? As I said, let me just go ahead and quote it to you. Okay, relativistic mass is called m, and it's equal to the following quantity. Okay, the relativistic mass itself is referred to as m, and in the numerator of the expression we have a quantity called m naught, which is referred to as the rest mass. The rest mass is the mass of the object if it is at rest with respect to an inertial reference frame. So for example, this 1 kilogram object that I have right here is at rest relative to me, therefore its mass is the mass m naught. However, now, let's say that object is moving at a speed v relative to me, an inertial reference frame. I don't see its mass as m naught. Instead, I see its mass as m, the relativistic mass. In the denominator of the expression, the v that you see right here is the speed of the mass relative to the inertial reference frame. Notice that the relativistic mass is greater than the rest mass. So imagine taking an object and say pushing it such that it accelerates. It's moving faster and faster. As it moves faster and faster relative to an inertial reference frame, it literally gets more and more massive. Now this doesn't mean that the object is gaining more matter. It's not like it's gaining additional atoms, protons, neutrons, etc., etc. No, instead it is getting more massive. Because remember what mass is, specifically inertial mass. Inertial mass is the measurement of inertia. The greater the mass of an object, the greater its inertia, the harder it is to accelerate. This has nothing to do with the amount of matter that an object contains. So if you take an object and you accelerate it such that it goes faster and faster, and it gets more and more massive as it does, this then means that it becomes harder and harder. It takes more and more energy to accelerate it even faster. Notice that this expression right here truly is an expression, if you will, of the cosmic speed limit. Because, for example, what would the relativistic mass m be equal to if the speed of the object v relative to an inertial reference frame was equal to the speed of light c? Notice that if v was equal to c, the denominator of the expression is equal to 0, and you end up with something for the relativistic mass that is undefined. It's literally of infinite mass. So then, therefore, how much energy would be necessary to accelerate an object up to a speed that's equal to the speed of light? It would require an infinite amount of energy to do so. So this expression right here is a true expression of the cosmic speed limit. Now let me go ahead and apply this expression here to the situation that we looked at in part 1, where we consider this one-dimensional perfectly inelastic collision. In order to do so, I have to take into account now relativistic mass. So now let me set this up in the following way. Okay, first of all, I'm going to go ahead and plug in my expression here for the relativistic mass. I'm going to put it off to the side like so we can go ahead and refer to it as we move through this situation. Okay, so consider now the following. According to O, the stationary observer, consider the situation from part 1. We have two objects of equal mass, and they are initially moving in opposite directions with the same speed. They collide and stick together and end up at rest. Let's assume that both objects are identical to each other and they have the same rest mass. We're going to refer to this rest mass very simply as m naught. So the objects have the same rest mass m naught. But each of these objects is moving before the collision with respect to the stationary observer O. So then therefore, the stationary observer O does not see their masses as m naught. Instead, that observer sees relativistic masses. So we have to calculate what those relativistic masses are equal to. So then therefore, let's picture the situation in the following manner. All right, the first object now, I'm going to call M1, where M1 is the relativistic mass of this object with respect to this observer. It's moving to the right-hand side with velocity v. Okay, then we have the second object. We're going to call this mass here M2. It's initially moving to the left-hand side with the same speed. Once again, however, we'll have to take into account a negative sign here when we add this up in order to find the initial momentum of the system. Okay, before we do that, however, let's go ahead and calculate these relativistic masses M1 and M2. They will in fact be the same thing because the speed of these two objects relative to this observer is the same value. Well, let's go ahead and write this out. So first of all, M1, this is going to equal the rest mass M naught and then divided by the denominator. The V here specifically in this expression is this speed. It's the speed of this object relative to this observer. So, okay, and then we have this mass here, M2. M2 is equal to the same rest mass, M naught, and then divided by the denominator. The V here is specifically this speed of this object relative to this observer. So then therefore, it's once again the same denominator as M1 from a few minutes ago. So now before the collision itself occurs, just as we did earlier, let's go ahead and total up the initial momentum of the system. We're going to call it P initial. Okay, so P initial is going to be M1 times V plus M2 times negative V. Let's go ahead and write this out, even though in fact it is equal to 0. We have M1, which is this quantity here from the relativistic mass that we just found, times V. And then plus M2, the same value, like so, that we just found, times negative V. All of this, of course, just adds up to 0. Like so. Okay, now, the objects collide and stick together. Think of this now as a single object. This single object is at rest now, after the collision, with respect to the observer O. So therefore, it's a rest mass. Let's call it capital M naught. Okay, so right here now is a new object. This object is at rest relative to this observer. Therefore, it's a rest mass. We're going to call it capital M naught. Remember that V final was equal to 0. So then therefore, before I explain further what is meant by capital M naught, let me just go ahead and total up the momentum of the system here after the collision. We'll call it P final. It's capital M naught times V final. V final is equal to 0. So this is equal to 0. Momentum is conserved according to this observer, just as it was in part 1 of the lecture. So P initial is equal to P final. And now let's focus in on exactly what is meant by the capital M naught. Capital M naught is M1 plus M2. Where M1 is this value here, and M2 is this value here. Add them together. That then gives you this value here. Notice that this value is greater than 2m naught. So what this expression is saying is the following. Let's say that this is an m naught of 1 kilogram. This right here is an m naught of 1 kilogram. When they collide and stick together, this object here is not a capital M naught of 2 kilograms. It's greater than 2 kilograms because of the denominator of the expression. So then therefore, let's just say it's 2.1 kilograms just for the sake of argument. So we have this 1 kilogram object here initially, this 1 kilogram object here initially, they collide and stick together, and this is not 2 kilograms, it's now, say, 2.1 kilograms. So where did that extra mass come from? It came from the initial kinetic energy of the objects prior to the collision. What you're starting to see hints of here in this calculation is the relativist expression for energy, E equals mc squared. That is showing that energy and mass are equivalent to each other. In terms of a real-world application, if you will, of this situation, what objects do we know of in nature, for example, that collide and stick together, and when they do, energy is released in some manner, or there's a transformation of energy in some manner? Nuclear fusion. So think of this problem here as sort of like a very bare bones basic example where we're setting up essentially a nuclear fusion process. Okay, now let's go to the bottom board and draw out the situation according to O prime. Okay, so on the bottom board here, according to O prime, notice that I kept our V prime calculations from the Lorentz transformation from earlier in part 1 of this lecture. We're going to need these guys here again as we now write out the relativistic masses of these objects relative to the moving observer O prime. Okay, so now, according to O prime, before the collision takes place, we have the two objects. This object here, M1 prime, now we're going to refer to it. It has a velocity V1 prime relative to O prime. M1 prime is a relativistic mass. We'll calculate it in just a moment. Okay, here's the second object. M2 prime, that's once again a relativistic mass, and then relative to O prime, it has a velocity that we calculated earlier, V2 prime. Oops, V2 prime, excuse me, is this guy right here. Make that change in your notes, by the way, if you had already caught my error. Okay, now before the collision takes place, let's go ahead and figure out what the M1 prime and M2 prime are equal to by using the relativistic mass equation. And then we'll total up the momentum of the system before the collision. So let's go ahead now and find M1 prime. Okay, so using the expression above, M1 prime is going to be the rest mass M naught and then divided by the square root. In the square root, the V here is specifically the speed of this object relative to O prime. It's the V1 prime that we calculated earlier by using the Lorentz transformation. Okay, V1 prime from earlier, however, was equal to 0, so then therefore this quantity M1 prime is just equal to M naught. This makes sense because remember how we're setting this up. We're setting this up such that O prime is riding along with this first object prior to the collision like so. So then therefore, according to me, I should see its rest mass little m naught, and I do. Okay, now let's find M2 prime. Okay, M2 prime is going to equal the same rest mass m naught, and then divided by our square root. In the square root here, however, the the V is specifically now this V2 prime. Like so. So what we have to do is we have to take this expression for V2 prime and then plug it into here. As you can see, this would get a little bit messy algebraically. So then therefore, I'm going to spare you the algebra. If you take this quantity here and you plug it into here and square it, and you simplify the expression that you're left with, you ultimately obtain the following expression. Like so. This comes out of the algebra that you would have to go through and blah, blah, blah to simplify when you take this expression for V2 prime and then plug it into here and square it and so forth. Okay, now on the far right-hand board, let's go ahead and total up the initial momentum of the system that is prior to the collision according to this moving observer O prime. Okay, we'll call this P initial prime. Okay, so P initial prime then is going to be M1 prime, V1 prime, plus M2 prime, V2 prime. And now let's just plug everything in. So M1 prime over there is equal to little m naught times V1 prime, which is equal to 0. And then I have M2 prime, which is this guy right here. Like so. And then multiply by V2 prime, which we found earlier from the Lorentz transformation. That's this guy right here. Like so. Okay, the first term is equal to 0, like so. And then in the second term, this guy here cancels out with this guy here, so we can go ahead and rewrite and simplify a little bit. And when we do, we end up with this rather messy looking expression. There we go. Like so. Okay, and now the collision takes place. Let's go ahead and find the final momentum of the system. All right, so in order to do so, let me do some erasing. Okay, then the objects collide and stick together. And now think of this as a single object, which I'm going to refer to now as capital M prime. This is going to be a relativistic mass that I'll calculate based upon its rest mass, which is capital M naught. We'll find that in just a moment. And then we have here V final prime, which remember we found earlier from part 1 of the lecture by using here the Lorentz transformation. Okay, now let's go ahead and find this capital M. Watch this. This capital M is equal to its rest mass, capital M naught, and then divided by the square root. Now, in the square root, V is specifically the speed of this object relative to this observer. That's this guy here, like so. So take this and plug it into the denominator of the expression, and when you do, you end up with this expression here. However, from the top bore, capital M naught, remember, is this. So take this and plug it into the numerator of the expression here. When you do these radical signs multiply together, that then gives you this. Like so. Okay, so now we have this relativistic mass, capital M prime. That's this guy here. Right here is the final velocity of the system after the collision, V final prime. Let's now go ahead and calculate the final momentum of the system. So the final momentum of the system is going to be P final prime. That's going to be capital M prime times V final prime. Capital M prime is this guy right here. V final prime is this guy right here. Plug it in and you obtain this. Like so. And now notice the result that we have. Right here is the initial momentum of the system. Right here is the final momentum of the system. Notice that they are the same. The momentum has been conserved according to the reference frame O prime. Note that P initial prime equals P final prime, as it should. So then therefore mass is relativistic. Because mass is relativistic, this then means that completely our descriptions of forces, momentum, energy, and so forth has to change. Okay, now go ahead and access the first example in today's lecture examples. For those of you in Honors Physics AB and AP Physics C, there are some additional problems later in that file. However, for those of you in Physics AB, this is the only example in that file. Okay, now, with respect to any sort of examples that you would see with relativistic mass, whether it comes to homework problems or the eventual assessment or exam for this topic, what sort of problems would we take a look at? Will we do anything as difficult as this? No, we'll keep it easy. So right now, go ahead and write down that lecture example. I'm going to go ahead and erase the board here. Okay, of course I'm going to keep here my relativistic mass expression. Okay, and then here's our problem. An object moves at 80% the speed of light with respect to a stationary observer. What is the percent difference between the rest mass and the relativistic mass? In other words, how different from each other are those two values if you have the object moving at the speed of light? Okay, so our object here has a relativistic mass m, and it's moving with a speed v relative to this reference frame of 80% the speed of light. In order to calculate the percent difference between the relativistic mass and the rest mass, it's like setting up a percent error calculation. Here's then how we'll do that. So the percent difference is going to be as follows. First of all, it's going to be the difference between the relativistic mass and the rest mass. The relativistic mass is greater than the rest mass, so then therefore I'm going to write this as m minus m naught in the numerator of this expression for that reason. And then in the denominator of the expression, if we were doing this as like a laboratory experiment, if you will, remember that always what goes in the denominator of your percent error calculation is the theoretical value or the actual value. In this case, the actual value is the relativistic mass m. So then therefore I place that in the denominator like so. Okay, now let me rewrite the relativistic mass m in terms of the expression. When I do, we obtain this. Like so. And now notice that the m naught there, the rest mass, it cancels from each term. So it cancels here, here, and also here. Keep in mind, however, that when it cancels out here, I don't have 0. Instead, I have a 1, like so. So then therefore, after I cancel out the m naught then, cleaning up the expression then gives me the following. Like so. And now at this point, I'm going to go ahead and plug into the radical signs there, the v equal to 0.8c. When I plug in v is equal to 0.8c here and here, all of the c's will cancel out. I'm going to do this in a couple of steps for us, however. My batteries are low. Okay, there we go. What I'm going to do first of all is just plug in v as 0.8c into each of these terms here and here. So 1 divided by quantity. 1 minus 0.8 squared. Once again, all of the c's cancel out. This guy here and this guy here is about 1.67. So now, let me go ahead and figure out what this quantity here is equal to, and then I'll multiply it by 100 in order to convert it into a percentage. So 1.67 minus 1, and then divided by 1.67. 1.67, there we go. Minus 1, and then divided by 1.67. My batteries are dead. Took the entire year for my batteries to die on that calculator. Okay, there we go. Here's this one. 1.67 minus 1, and then divided by 1.67. Quantity multiplied by 100. And this works out to be about 40%. So it's a significant difference. So once you start to reach relativistic speeds, the relativistic mass is significantly different than from the rest mass, and then therefore we do in fact have to take that into account when setting up situations in dynamics. Okay, now this concludes the lectures on relativistic dynamics for Physics AB. However, for Honors Physics AB and also for AP Physics C, there are additional lectures to come. Today's shirt is ABSU.